大家要是前面介绍高级，小丽不会是我，到时候查一下销售数量，全球现在做多少？
我们这几天都来出一次，
还是没有，我直接来深圳，
还有买这个线下的，
几天没见过。
发下深圳。
是啊，
来我有了几天。
没有，确实5月前的，好像这样子第一学期。
今天发现，如果60寸的耳机电池可以调成
对，也还是少。
但是60
他们的亚太地区高级技术顾问要我，然后就在丢数据。
只有30，
我也觉得。所以我今天去给我朋友买东西，我说我们报一下这个 case。然后不行，然后这个事情得去上市了。
他会提供那个，
这是啥？很有切心地的。
哦，对。
我今天因为我看，我感觉他更偏爱辣椒的大一些，有它不可能它实现标准。
为啥呀？这个。关注不是一个东西。
不是，实际就是标注磁带啊，是吧？
这就不是一个东西，就不是一个东西。
对啊，可能不能去喜欢一个。
你做不了这个，别想。
挺贵的，你去。
挺贵的，就是你的算力逐渐
大元模型，就那个模型没公布，然后那个
就是它
要实现的算力你也没有，
而且它用的也就是这两个，就是那个
就是大力出奇迹的，几千亿枪，
对，几千亿吧，人家这个理解看起来像是理解，现在确实跟这软体3实验室就来做模型的人会很多。
确实。
咱们只能干干。
我写了几个很骚的程序。
怎么说？
比如说这个东西批量给视频加字幕，就是这个东西就是给油管上视频加字幕，然后生成这样的文件，就比如说
字幕文件吧。
对，把字幕文件从字幕文件中拉起来中英文，就是双语，就可以说。
油管可以自带字幕了，
但是你不能整段都摘出来，你只能一句一句的看。
你直接把那个明白了，我明白你的意思。
然后再配上大电视，然后看，小的看着贼舒服。然后课后，这到5点开始是一条龙。只有2门课是语文标准，有1门课就是那个首先理论的，但是用不住。他录了，但是他们收音听得贼差，有时候我根本听不清楚。
我过几年，我说实话，我过几年我想换听歌，我还真得问可以怎么搞。我估计我先得 report Allen，然后 Allen 再告诉我在学校会。
不行的话，就给他买一个好一点的
学习，我感觉就是2年的方面。
Hello. Let's begin the class today. So I actually find there's like much fewer people in the campus recently. Not in this classroom. The classroom is still full. I'm kind of like wondering what happened. Like in the morning when I go to breakfast or during the lunchtime, it seems to be significantly fewer people. Like the queue is shorter than before. You guys notice that? Like originally it was like 10 minutes or something. Now it seems the queue is much shorter, I would say. But I don't know. Maybe like it's the tourists, or like I have a bad assumption about this. Is like, are we like only going to have the passion for classes for like 2 or 3 weeks? Then after that, when I see you guys for the next time, it's already like 1 week before the final exam or something. So it's like the peak and then goes down and then peak again. Anyway, so speaking of the final exam, I think we will release the plan on like week 5 or so. So we'll have our TA here, and she will be introducing to you guys what's the final project looks like for this year. But like, don't be nervous. But it's always like a good advice is like it's never too early to start to find your teammates, to find your friends. But like I think I got asked this question a lot. It's like if you can't find your teammates, it's okay. We will be help you to find a team there. But due to the number of students in this class, I think in the end of the day we probably will have like 5 to 6 or something. I will check with the TA. Okay, cool. So today we're going to start a very important thing, which is the computational graphs, and I think this is a very, very useful abstraction that will be used for the entire class. So in the old days, I will tell you the story. In the old days, we will need to write, the back propagation or this optimization code on our own, and it's like very, very easy to make a mistake there. But these days, given like we have PyTorch, TensorFlow, those kind of things, which are built on this abstraction of computational graphs, we will only need to learn, how to draw this kind of graph, and the software, for example, PyTorch, will automatically does the back propagation, change the parameters for us. So it's much, much more convenient than the old days. And then we will finishing this session of discussion by pre-training and fine-tuning. So when I was first teaching this class, I have this ambition that I will be teaching, finish teaching BERT even before the job period of the class, so that even you drop the class, you come out knowing that what happened in BERT. At that time, there's still not there isn't GPT-3 yet, but I still think to put the BERT on the very beginning of the class makes sense, because it's really not that difficult. and it really helps you to get a high-level idea of what is actually happening in the NLP field at the moment. So last time we were talking about training an RNN language model. This RNN language model can, in theory, considering or encoding infinitely long history for your sentence to predict the next word. So for example, here if I want to predict the students opened there for the next word, what is the next word, then I can consider basically the full history of that sentence. So the students opened there. These 4 words I can consider them all. So the trick here is basically we'll be finding this H2. So for example, when we compute this H2 here, so H2, the computation of H2 is built up on the input embedding here for students, which is E2, and also built up on a recurrent setting. That's why it's called RNN, right? So built on a recurrent setting of H1. So H1 and E2 together, like after some computation, we use WH times H1 and like WE times E2, and then plus some kind of a bias, then we get this H2 basically. So H2 naturally contains information from its own context, which is students, and also like contains information from H1, which basically encodes every bit of history before this word number 2. So H3 and H4 for sure. So we get a rough idea of that. When we build up a language model for training, we will need to have a training objective. We'll need to have a loss, right? So, and based on this loss, we're going to adjust the parameters inside this huge neural network. It can be huge, it can be small. Inside this neural network, WE and WH and all these parameters will be adjusting those parameters so that the entire model does a really good job in terms of predicting the next word. Because like during the training, we actually know what's the next word. So for example, Z here, the Y1 output should be students, right? Students here, the Y2 output should be open. We actually know what happened. So this is separatedly as like, you know, like here is like 4 different classification, multi-class classification problems, like 4 different logistic regression it seems to be. So the first one, the input is Z, and like, you know, given previous is nothing, and we want to classify it into the one class in the multi-class classification, and the class name is students, right? Here is like the input is students and previous history, and we want to do a multi-class classification problem and classify that Y2 into the next word, which is open, right? So this is some kind of understanding for these 4 steps, and of course, like, you know, in logistic regression, you take the final one as your prediction, as your like loss, and in you know, recurrent neural network here, it's just summing up them all so that it actually can perform a really good job in terms of predicting the next word. Okay, so any questions? This slide. So, like, you know, recover a little bit memory from the last lecture. So we said that this is a computational graph, but we never like, you know, give it a formal definition of what this like, you know, figure is talking about. So today, what we are trying to do is we will draw this figure one by one and let you know what, you know, elements are inside this kind of computational graphs. First of all, there are more than one ways of drawing computational graphs. As long as you know, the conventions, it should be easy to you what this you know, figure is talking about. So let's see a very, very easy example first. So this is logistic regression. So everyone knows logistic regression already, right? Classification problem. If you know this, let me know. Studied this before in the machine learning class. It's very, very important. Okay, okay. I think only half of the students know this concept. It's actually very, very simple. So basically, I think it's the easiest thing, or like it's the best thing that the machine does, which is like give some kind of input, and then you give an output, which is the prediction of class 1 or class 2. So binary classification is like logistic regression. So basically, if I give you the, say, temperature, say the daylight hour, say it's raining today, those kind of features, and x1, x2, x3, x4, those kind of things. And I want your model to output if tomorrow going to rain or not, right? So you have a binary decision of if it's rainy for tomorrow, okay? So what we do is we just build a very simple model for that, where like we have this x1 is probably the first feature. The first feature is if it's raining today, for example, then x1 can have two values, one is 0 and one is 1. And x2 is like the, for example, the daylight time of today, okay? So for example, it's 4 hours, and it's a real number, right? So you can put 4, or you can put 5.5 hours, something here. So these are the two inputs, okay? So we'll give it into a form of W1x1 plus W2x2 plus B. And then we can compute this H1 here. And then we put this H1. People know what this function is. This is sometimes people call it a sigmoid function. This is very similar to softmax function. It's but I will talk about it later. This is a sigmoid function. This basically will having this number into 0 to 1. Okay, so this means the probability that y equals 1, which basically if tomorrow will be rainy, so the probability of if tomorrow will be rainy is from this function. So P1 actually equals P y equals 1 given x1 and x2. Okay, so everyone knows how we compute given like W1 and W2 and B. Okay, so all these numbers are given to you. You x1 you know, x2 you also know. So for example, x1 is 1, x2 is 4.5. Then you know how to compute the probability for if tomorrow is raining or not, right? This number is between 0 to 1. Okay? Cool. Questions? Yeah, I think half the students don't know those questions, but like, do you have any questions on this slide? I probably will ask a question. Why there's like red color and blue color and black color there? Why W1 and W2 are red, B are red, these things are red, and these things are in blue color? Why?
These are the parameters.
Yes. Okay. So that's actually, I do it intentionally. So W1, W2, and B are the parameters inside this model, right? So basically, when you train the model, you want to modify the number. You want to adjust the number of W1, W2, and B so that it can achieve a better accuracy in terms of predicting y. Right? Right. Okay. So H1 and P1 is more like expression, right? So based on the input and the parameter, you should be able to compute those things without any difficulty, right? Because I tell you, this is how it's computed. This is how it's computed. Okay? So we draw that on the graph. We have many different ways of drawing a graph, I will tell you. But like, it's simple, like we follow this convention. We have input x1 and x2 are two nodes, and then we put in some kind of computation on top of it, and then we get h1, and we will do a computation based on h1, then we somehow get p1. Simple? Easy? Okay, so how we compute the probability for another thing, which is P2, which is y equals 0. It's the binary classification problem. So P2 is actually also simple. It's basically 1 minus P1, right? Because it's either class 0 or class 1, which has to sum up to 1. So just using 1 minus this thing, and it becomes a number like this. And previously, this H1, you can also compute it. It's still H1, and then put in H1 here. So in the end of the day, you'll get this. So for this, if y equals 0, then the probability of x p of y equals 0 given x1 and x2 is computed this way. Questions? Questions? In logistic regression, how we train the model? In logistic regression, how we train the central model? How do we know if what is W1 and W2 and B there?
Loss function. Min max.
Sorry?
Min max is the loss function.
Loss function. What is the loss function?
交叉值。
Okay. Cross entropy, right? Yeah, there's a cross entropy loss. So the intuition should be simple. Let me see if I want to another thing here. I think I do think some students feel a little bit confused. So let me get it. This far. Anyway, basically, this is how we train supervised learned model, and the L here is a loss function, and theta here is the parameter inside this model. So this is a very general form. Okay, so it's a very general form. This form tells you what? So we'll be finding some theta, which basically we'll be finding some parameters that works the best on this objective here, on this loss function here, right? What this loss function is telling you? So basically you will be having a training set. This training set contains examples that maps x into y. So xn and yn here is one training example there. So for example, you have some students who annotate a bunch of like movie reviews for you. So some of the x's maps to positive review, some of the x, which sentences, maps to y, a negative review. So you have a bunch of that. This is your training set, right? So you kind of build a function, then this function is fxn with the parameter theta. So this function can be of many forms. So for example, what we have is the w1x1 plus w2x2 plus b, and then we put it into some kind of a sigmoid function, and it gives you a guess, right, of the class label. So it's either 1 or 0. Okay. Okay. So yn here is actually the gold label. So what you want to do is you want some kind of a theta that always doing a good job in terms of fxn should be equals to yn, right? So if we say the prediction here is like fxn equals to yn hat, and this yn hat should always equals to yn. Okay, so this is the form that we are trying to do here. And this side is a loss function. And what this loss function is telling you? This loss function tells you if your prediction equals to the gold label yn here, you don't need to pay anything. There's no price that you need to pay. If it doesn't equal to yn, then it means you did a bad job, right? So you will need to pay some price. So the training procedure is basically give you this kind of loss function. This is one of the loss function we have. We can have different loss functions, but loss function basically tells you how much price you will need to pay if you do something wrong. Okay, depending on how wrong it is, you can have different loss functions. And then what you want to do there is you will adjust the parameter, which basically learn the parameter, see that there, that does the best of like having this function fxn mapping to your final result y. Okay, so in logistic regression, this is essentially this case that we're trying to do there. So basically here, what we do is in y equals 1, this is like y equals 1 case, so which means like yn equals 1. We have the goal label, which is equals 1. And in this case, we'll be computing the loss that we incur in this one single example, right? This one single example here is how to compute this. Is we'll be putting x1 and we'll multiply that with w1. We're putting x2 and we will multiply that with w2, and then we'll putting them together and plus this b there, and we will be able to compute the h1. And then we're putting h1 into a sigmoid function. It gives us p1, and we take the negative log of this p1, so it gives me a final loss function. So for example, if p1, which is basically, what is p1 here? What is P1 here? P1 is the probability of y equals 1, right? So if we put in a negative log over P1, then it's what? It's a loss, right? So we want this number to be high or low. We want this number to be high. Right, so that we want this number to be high. So that we want this number to be low, right? So basically, the better this model predicts, the less loss it incurs, right? So for example, you have P1 equals to 0 here. Unfortunately, this is a 1 case, but you have P1 equals 0. Then what you do? You pay how much price you pay there? You pay log P1 equals to minus infinity, right? Yes. Log 0. Yeah. And then negative log, negative, this is like, right? Remember that. So we actually incurred a very, very, very high price that we pay in there, right? So if we actually, have P1 equals 1, then we actually incur a very low price, which is 0. Okay, so this is basically the thing you want to do there. So okay, so what you want to do is based on this example. Based on this example, you want this number to be small, right? So somehow it's changing this W1, B, and W2 to make this number small, right? It's like a toy. Then I have like twinkle here, and I twinkle here, and I twinkle here. I can't change the input because the input is fixed, right? So twinkle some here, twinkle some here, twinkle some here. This is 5. I change it to 4, and then like this number somehow is lower, right? So this is what I'm trying to do there. But I want to have a better, more theoretical, justified way, a better way of doing that. But you get the point, right? You're just changing those red numbers, and final loss will be lower, and the model will be better, right? This is the case. This is what we are trying to do there. Okay, so this is a general case, actually. So if I'm given like a multiple different examples, or if I'm given like y equals 0 other cases, it's actually easy for me to compute the final loss there. The final loss is the negative log probability, right? Okay, so basically this will be a general form of computational graph. So inside this computational graph, what we have the input, which is the black things, x1 and x2. This is just for one single example. You can imagine that if you have like a lot of different examples, you can put a lot of like this small graph here, and in the end of the day, you will be having a summation on their loss. No, right? So if you have multiple examples, this is also easy. Then you have what? Parameters. Parameters is W1 and W2 and B, those things. Okay? So you have the expressions. The expressions is in blue, where like this is expressions. It's not the real number there. I mean, it's like some number that computed along the way, right? So you will be compute those numbers, but it's not like having a physical memory place that stores those things. Okay, and you have the operation, which you have like sometimes this times operation, this multiple operation takes 2 arguments here, and this plus operation takes like 3 arguments here. All these things, and you have sigmoid. Sigmoid takes 1 expression here, and you have minus log. Minus log also only takes 1 expression here, so it's negative log p1, right? Then you compute some kind of a log. Okay, easy. So one thing to remember, there is one thing that's special, which is inside one computational graph. There is one and one only loss node. This is the only thing that you will need to remember. So in this computational function, in the end of the day, however you compute, you will be computing one loss there. And what we are trying to do is, by changing those parameters, this loss can be different numbers, right? What we're trying to do is we'll be finding the best way of changing those parameters so that the loss is minimized, reach a very low number. What does it actually mean? It means your model is doing quite good, right? Because it's not paying quite a lot price on this kind of thing. Okay? Any questions? Yes. Is also in the parameters. So you see this way, h1 actually equals to w1 x1 times x1 plus w2 times x2 plus. Okay. Any other questions? Everybody knows what we're trying to do there. Very important thing. Only one loss. Okay. So this is all. This is actually all, because now why you draw this computational graph is because like you want to learn W1, W2, and B, those parameters, so that it has a really low loss, right? So that it leads to a really good model. And how you build this computational graph? It's from your model, right? Your model have like ways of computing the probability of some kind of a class in the classification problem in the logistic regression, right? Logistic regression, this is what we do. This is essentially logistic regression, okay? So, and then one natural question you will be asking is, after this, how do we change W1, W2, and B so that it achieves the best loss there, right? So this is a natural question that you should ask. And then, if we know the answer to this, question, we have a model. We have a model, right? So I give you a bunch of training data. I give you only one training data, you can just build this. If I give you two training examples, you will draw another graph here, and it has another loss. And I give you another training example, you get a third loss, so on and so forth. And in the end of the day, you just have them together to be the final loss, right? So it's like, you know, everyone is paying some price, but in the end of the day, I want the model to pay minimal price at this training set, right? Okay, so only question here is after I draw this graph, I think it shouldn't be difficult for us to draw the graph anymore. After we join the graph, how we compute W1, W2, and B. Okay, so the answer to this question is actually quite simple. So for example, if you are trying to draw this graph in Python, then what you do is you say, I have a computational graph. Say CG, right? And CG should add some node. I'll just write something here. And add node x1, add node w1 as the parameter node, blah, 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 blah. And basically you draw something, right? You draw a lot of things, CG, for CG. So this is drawing this graph in your lovely programming language. And this CG now contains the graph described here. Okay? So it only have one loss node, right? So how we get the parameters for that is we'll just write CG.trend and done. That's all. Okay? So the how to search for W1, W2, and B, the computer will do it for you. Easy? As long as you can draw such a graph, and as long as you know how good is good in your task for this model, then W1, W2, and B are computed automatically. Imagine. If you want to run that on GPU, then you probably write something like set device GPU1, and then using this, and that's automatically checked for you. It's not like the full story, but more or less, it's like this. It's quite simple. So in the old days, we were developing something called DYNET, D-Y-N-N-N-E-T. So it's like an early programming neural network programming toolkit, kind of the same as PyTorch. And then this is what we use there. So after we join this graph only have one loss node, and then we will be able to adjust the parameters just fully automatically using the computer. Okay, you can have a rough idea here. The intuition here is you should be able to find those parameters that's the best in the loss. Okay. Right? You should be able to find those. Okay. So how we find those things is actually we use automatic differentiation. So this is optional. You don't need to understand things here. But I'll just tell you what actually happened. So basically, if you want to get the best W1, W2, and B, you actually want to compute the updates for these things, right? So W1 is equal to W1 plus some update, right? So this is the update you're trying to compute there. So if it's +1, if it's -1, if it's +2, if it's -2, some kind of an update there, right? So in the end of the day, how we compute the update is we'll be computing actually, people know this before, gradient descent. So this is like the typical textbook example when we're talking about logistic regression, is we will be using the gradient descent to update the parameters. Okay. people know this? See this figure before? Not many. Okay. Okay. So this is saying what? This surface is the loss function surface. Okay. So basically, you will be having two features here. One is x1 and one is x2. Forget about the xy. It doesn't matter. So so basically, so the higher this, the larger this z number there, the more loss it actually incurs, right? So you actually will be changing W1 and W2 so that in the end of the day, it will be going to a very, very, very low thing, right, on the surface, which is like, you know, incurring like little loss there. So this is like, you know, fog in the mountain. So basically, at each step, what you are trying to do there is you will be following the, right? So be taking the gradient for this thing, so going down really, really fast, checking like, you know, the fast go down way at that position and goes down follow that way. So there will be like, you know, a step size, which basically is like how large you want this size to be, and also it has this kind of gradient thing, which is like it marks the direction of the fast going down mountain direction, right? So this is by differentiation on the loss function with respect to theta. So this is how we get it. And then basically we'll change this theta, whatever theta this is, to be the theta that goes down the hill. So in first, I might be here, and second I'll be here, third I'll be here. By updating these things, I'm going lower and lower to that mountain. So this is gradient descent algorithm. When you discuss like logistic regression, this is what we discussed there. And for this neural network, it's actually even simpler. We will just need to compute this gradient for this W1 with respect to the loss function, and then move towards that direction, right? So the only thing is what's the direction for this looks like? What's the gradient for this W1 looks like? And it can be computed using this automatic differentiation, where basically we have a chain rule. If we want to compute this thing, sorry. How far did I go? So you have some kind of upstream gradient, and you have a downstream gradient, which is like going that way, and you have some local gradient, which is like, you know, compute the gradient with respect to h and z. And then you just time them together so that you get the gradient from this s with respect to z there. So basically, it's kind of a flow where you want to compute the gradient for this one, and the loss function is actually here. And then you first compute this. So loss given P1 and then P1 given H1, and then H1 given W1, right? So you time all these things together, it becomes loss with respect to W1. Okay? So every step, it's actually simple for you to compute. Basically, after you define what's the operation on these nodes, it's actually simple for you to compute loss given P1. It's actually simple for you to compute P1 given H1 with respect to H1, and it's also convenient for you to compute H1 with respect to W1. So it's like a flow. We say flow back, and then the gradient will flow to each of the things. So each of the nodes can receive a gradient. Okay, so you actually, after this, you know how to change this W2 so that you can achieve a lower value of loss here. This will tell you how to achieve a lower value things here. So W2 will be equals to loss with W2 times some step size plus your original W2. This will be the updating rule for this W2. Okay? So it's the same thing that we are doing. It's just we're doing it in different way. So originally, when we were in the case of logistic regression, you know, we will be told that like we can compute this in a closed form, right? This is a closed form thing given those things. And then if we join the graph, we don't compute it in closed form. We compute it using automatic differentiation, which will be involving 1, 2, 3 things. But in the end of the day, these 3 things times together is actually the closed form solution for that parameter. Okay, you get the idea of how we adjust the parameters so that the loss is minimized. If you don't get it, it's okay. If you don't get it, it's okay. You understand that when we build the loss function and we just handle it to the computer will be able to compute all the back propagation, those things for us. So in the end of the day, it will give us a best parameter for W1 and W2 so that our loss is minimized. Okay? So in these days, it's like very, very little cases we'll still need to write the back propagation anymore. So we don't need to write it. We just need to write the forward. So if you're familiar with the neural network textbook, this is the typical example for forward and backward algorithms, right? So the forward pass looks like this, where we have the input and parameters, all these numbers, and we just want to compute what's the final loss. This is the forward pass. And backward pass is based on the forward pass. We'll be computing all the gradients for each of the parameters. So this is the backward pass. So then we do the parameter updating, right? Based on the result from the backward pass. So this is the when you hear people talking about forward backward algorithm in neural networks, this is exactly what happened there. Okay, so if you don't understand how we compute the gradients, it's also fine because you just need to understand when we having such a graph, when we know how to define the loss, we actually can train a model in this way. The computer will do it for us automatically. Okay? Questions? No? Ready? Yes.
How do we set the original value of W1 and W2?
How do we set the original value of W1 and W2? So in logistic regression, how we set the value of W1 and W2? One. Randomly, right? So random initialization, right? So we can randomly initialize them to be some kind of a number around 0, and then we start from there. Then we do the gradient descent and we find the best one. So basically, this is random start means what? Means you are randomly starting at one of these places and you're trying to go downhill, right? So you should be able to reach some kind of a place in the end. So this is the same thing. We just randomly choose the initial value of W1 and W2 and all these parameters. We just don't just one thing, don't set them to be all 0. Because sometimes it's inconvenient for for computational reasons. Yeah. Other questions? Other questions? Other questions? No? Yes.
So we don't need to achieve the whole process by our own.
No. You just need to how to draw this kind of thing, and then it's done.
We just need to set the learning rate
Yeah, the learning rate, yes, of course. There are a lot of like things like we will be need to choosing, which is the hyperparameter, all those things. But you know, in theory, when you choose the step size, right? So like how much you want to adjust the parameter here, then you're doing a good job. Okay. Good question. Yes. Other questions? So one question I got previously teaching this class is, what if we do this? What if we remove this thing, and then we say we have the final loss as just the negative P1. Is this okay? We can have different choices of like loss functions, right? So what I do is I will just negative this and put it a loss here. So what happened is when I do it correctly, this will be a smaller number, so -1, right? When I do it wrongly, this negative will put it into 0, which is like relatively higher number there, right? So is it okay to remove the log here? Yes? No? How many people say yes? How many people say no? Okay, so for not yes and not no. Who didn't raise your hand? Raise your hand now. Who didn't raise your hand? Raise your hand now. Okay, yeah, okay, yeah. So why yes? Yes, people? Why? Why do you think it's okay? Or I should ask no people. Why no people say it's not okay? Why?
The speed of convergence.
Sorry?
The speed of convergence may be too slow.
The speed of convergence may be too slow.
Yeah.
Interesting. Why?
Because the gradient of the sigmoid function is rather smaller than the log one.
Interesting. So, so he's saying like if we change that into this kind of a loss here, then the gradient might not look quite okay. So in the end of the day, we probably will have longer training time.
Yeah.
Right. So other justifications. This is all what you think. What do you all think? Why? Why other people say no? Okay, so that's actually nice because you all agree that this is also something reasonable, right? It might be slower. It might not be the perfect as like minus log or blah blah those things, but like in spirit it's correct, right? In spirit it's correct. Why? In spirit it's correct because you want to adjust those numbers, and when you adjust those numbers, when the model does better, you need to pay less, right? So if I'm changing it into something like this, then it's a problem. If I'm changing this into, say, positive log, then this is a problem, right? So it actually means the worse that your model did there, the lower cost it actually paid, right? This is not good. So theoretically, as much as you follow the philosophy that when you're adjusting your model, the model does better, the loss is lower, then it's actually okay, right? But also you will need to have computationally thoughts, because some loss functions may be may be easier to work with, may be more convenient for this optimization procedure than others. So one thing that we remove the log function, if we remove the log here, it's actually a good example. if we remove the log here, then what happens? Then if we say for a large number of, I can't draw anything for it. Then for a large number of things, so for the entire training set, we'll be having P1 times, sorry. Anyway, so for that, we'll be having P1 times P2 times P3 times P4 for all these different examples, right? But then, like, P1 probably equals to 0.2, and P2 probably equals to 0.5, 0.3, something. And when you multiple a lot of different things, small numbers together, you'll cause underflow problem in your computer. So that will be too small a number. But if you put it into the log space, then it's like -1 plus -2 plus -100, whatever, those things. Then you actually have a negative large integer number. So this one you have a more better precision to work with. So this is why people love to put log there. This is one reason. And some of the other reasons is like you will take the gradient. Some of the functions are easier for you to take the gradients than some of not. So for example, if you have this 0, 1 cost here, which is this black thing here, this is 0, 1, means that if you are doing it correctly, you get 1 score. If you are not doing it correctly, wrongly, then you get 0 score. Which means if you are doing it wrongly, you pay 1. If you're doing it correctly, you don't pay anything. So this kind of things is like it can be differentiated at this age, right? So it's a discontinuous function. So if you're putting this kind of operations into your computational graph, then it actually is very difficult, if possible, to work with the differentiation procedure to get your gradient computed that way, automatic differentiation, right? So we also want some function which are easier for us to work on the differentiation version of that. Okay, so only two more or less like practical choices of how we choose how to compute the loss. So we have many different loss functions. Some of them you might be heard that before. So hinge loss is actually the loss that we use in SVM. Log loss is the log loss we just used. We have the 0, 1 loss, which is kind of an ideal one, but it's really hard to optimize. We also have many other different things. Okay, any questions? No? Then we'll have a break for 2 minutes, then we'll come back.
这个课程2个